starting with Justin Hom, who's going to tell us about the reference star vetting for the Coronagraph instrument and beyond.
All right. Can everyone hear me okay? I can't really hear myself, so it's kind of strange. But OK, yeah, thank you all for being here. Thank you to the SOC for giving me this opportunity to present some of what I've been working on. My name is Justin Hom. I'm a postdoc at the University of Arizona, and I'm also the lead of the CPP Reference Stars Working Group. And I'm here today to talk to you about what these reference stars are and why they're so important for CGI and potentially other future space-based high-contrast imaging missions. So before I get going, I just wanted to quickly shout out all of my working group members and the several external collaborators that we work with. This wouldn't be possible without the hundreds of hours these people have put into taking observations and doing data analysis. OK, so a standard CGI observation starts by digging a dark hole on a bright reference star before moving to your science target. And after taking some images of your science target, you go back to your reference star, take some images, and sometimes you may need to sort of re-optimize or maintain your dark hole contrast, and this cycle sort of repeats. So this is a required part of every CGI observation. Now, at the same time, we can also take some science camera images of our reference star and use them as post-processing RDI references. But we can't just use any star as a reference star for CGI. So there's a really strict set of criteria that a reference star needs to satisfy. And I'm not going to go into a ton of details about why each of these criteria are the way they are. You can ask me afterwards. But yeah, they need to be extremely bright. So our threshold is third magnitude in V. They also need to have really small resolved stellar diameters. So our current threshold is 2 milliarc seconds. And they also can't have any companions, and they don't have to be bound companions, that could possibly degrade your performance. And to show an example of this, these are sort of example plots of the PSF profile of an off-axis companion, and showing how much flux that PSF profile could introduce into your dark hole and possibly contaminate it. And this next criteria is not really a criterion on reference stars, but more so on science targets. So your science targets have to be within 5 degrees of observatory pitch angle from your reference star. And what is pitch angle? So this is a top-down view of the observatory. And so you can think of the pitch angle as kind of like this up and down motion with respect to the bore site. So this doesn't really leave a lot of options. There aren't that many super bright stars that also have really small diameters, right? A lot of super bright stars are pretty close by and relatively well resolved. And guess what? Out of the ones that remain, they're all high mass stars. And if you know anything about high mass stars, you know that stellar multiplicity rates are extremely high. So what are the consequences of possibly picking a bad reference star for your observation? Well, we're sort of expecting degraded performance. So in the best case scenario, you may get really poor post-processing performance through RDI. In the worst case scenario, you could get sort of a dark hole digging failure. So you won't be able to dig down to your desired raw contrast. And the net result of all of this could be several wasted hours. And we have very limited time to use CGI. So we need to make sure that we're picking good reference stars for our observations. And sort of this last thing that I'm going to touch on a little bit later in this talk is reference star availability. So given that we have a very limited number of reference stars, there's a decent chance that reference star availability at any given time can strongly dictate when you can actually observe your science target. OK, and so to tackle this problem, the CPP formed the Reference Stars Working Group. And the Reference Star Working Group manages the Coronagraph instrument for the Coronagraph Instrument Reference Stars for Exoplanets campaign. And our primary job is to create this reference star list. And so we combed through catalogs and literature references. We left no stone unturned. And we came up with a list of 40 reference star candidates. And we also have a backup list of about 18 or so that have slightly larger diameters than our threshold. And we'll go to those in case we happen to run out of these 40 primary reference star candidates. And here they are distributed on the sky. This is in ecliptic coordinates. And the colors actually correspond to what are called ranks. And so, not all of these reference star candidates are created equal. There are varying degrees of evidence suggesting that, these reference stars could have a companion around them that may be problematic for us. And so rank C is, highest likelihood or highest evidence that there may be a companion, but, so far not confirmed. Rank A is, it looks pretty good. Now, these rankings were mostly based off of archival indirect surveys, so like RV or astrometry. But the problem for these specific targets is that a lot of these measurements are not very reliable. And so what we really need to do is direct imaging to assess whether or not these reference stars are actually suitable for our observations. And really, we need direct imaging down to the Roman requirement. The state-of-the-art ground-based high-contrast imagers and interferometers can get us the closest to this Roman requirement, but not fully. But it also takes a lot of observing hours to observe all of these reference stars with all of these types of observation methods, and we don't have a lot of time until launch. So, as sort of a precursor to doing deeper vetting, we started off by doing moderate contrast vetting using speckle interferometry and AO imaging. And this is just a really efficient approach to quickly vet all of our reference stars for anything that is sort of obviously bad. So we were able to survey about 80% of the total primary and reserve list. And good news, we did not find any companions. So that's a win. So I'm showing some example data sets here. On the top, this is an AO image from Faro at Palomar Observatory. On the bottom, these are reconstructed speckle images from Alupeki at Gemini North. And in general, we were able to achieve about 5 to 7 delta magnitudes of contrast sensitivity across all of our observations. And particularly within the sort of field of view of Roman observing modes, which is what we're really interested in. Okay. So, with our full sort of list of 40 reference stars, I want to get into what I mentioned a little bit earlier about schedulability and visibility. So, not every part of the sky is visible from the observatory at all times of the year. So this is a map of the sky in ecliptic coordinates again, and it's colored by how many days during the year that piece of the sky is visible from the observatory. Now, if you remember, for CGI observations, not only does our science target have to be visible, but our reference star target also has to be visible and must be within this 5-degree delta pitch requirement at the time that you want to observe it. So that's a lot of things that we need to try to capture. So to help simplify that, let's define a scheduling efficiency. And this will be the number of days your science target is visible and has an accessible reference star, divided by the number of days in a year that science target is just visible by itself. So if we have all 40 of our reference star candidates, things look really good. On average, our scheduling efficiency is about 95%, and it never dips below 80%. So, most of the time, we're not bound by reference star visibility in this case. Now, if all of our rank C reference stars turn out to be bad, like have problematic companions, we only have our rank A's and our rank B's, that gives us about 20 options, but it's still not bad. So on average, we still have about 80% of this scheduling efficiency. Now, if all of our rank B reference stars also turn out to be bad, then things also start to look really bad for scheduling. So we only have 4 rank A reference stars, and so understandably, our efficiency plummets. And on average, we only have about 30% efficiency, but it never goes to 0. So there's never any part of the sky that becomes completely inaccessible due to only having a few reference stars. So this is great, but as I mentioned before, we really need to go down to the Roman requirement, and the only way we can do that is with ground-based high-contrast imagers and interferometers. And since 2024, we've been sort of amassing all of these observations. We've collected about 300 plus, I think it's actually up to 400 plus hours now, of ground-based observing time across several observatories, across several instruments. We've been collecting all of this data, and I want to highlight the work of some early career researchers here who are specifically leading some of these observing programs and working on this data. Nick and Macarena are also here at this conference. They had posters up the past couple of days, so hopefully you got to see those as well. And with all of this mountains of data that we have, we can now start to really assess reference star suitability for our observations. So this is one of our reference stars, Beta Librae, and we've collected detection limits across all of the observations we've been able to collect, all sort of coalesced onto this very messy-looking plot down here. And this is what I would consider a fully vetted reference star. So we have the deepest limits that we can achieve from interferometry in the sort of smaller than 100 milliarc-second separation regime, and the deepest limits we can achieve from high contrast imaging in the greater than 100 milliarc-second regime. And we want to achieve this for all of our reference star candidates, and the good news is that we're set to do this by this fall. So by the time launch happens and by the time the observation phase happens, we will have a fully vetted list of reference stars. Now, with all of this new information in hand, we actually recently went back to reassess our reference star rankings and modify how we think about how suitable reference stars are. So for one, we're going to remove any reference stars where we found new stellar companions. And there's been a handful that we've seen from our deeper observations through both high contrast imaging and interferometry, a couple of these that I wanted to highlight here. And we're also going to think about a couple other additional factors that may be bad for reference stars. So first is to remove, or in some cases, just deprioritize reference stars that have high infrared excesses. So infrared excesses are indicative of circumstellar dust. And we've done some recent modeling work on these particular stars with infrared excesses that suggests that their circumstellar dust disks are actually pretty bright. And that's going to be really bad for post-processing RDI performance. And we're also going to deprioritize but not remove any stars where we still need additional observations to sort of get that full vetting of those reference stars. And so since applying all of these new rules, we've eliminated 5 reference stars entirely from consideration. But this is all still in flux. We're still taking observations. And so that number could easily go down, or rather the total number of reference stars could still go down. Okay, so what about planning our observing campaigns? So, we're on we're on track to get all of our reference star vetting done by this fall. But as Skylar sort of alluded to, we really need to plan our observations now, pretty much, at least for our first 6 months of observations. So to do this, we're going to sort of remove the inherent risk of our rank C reference stars, only consider ranks down to rank B. And this leaves us with a list of 17 that we feel relatively comfortable with in terms of planning our observations. Here they are in the sky. But it's important to emphasize that this is not the final list. So we're still taking observations, and the list is ever evolving and changing. And so our work still keeps going, even beyond our first sort of planning of the first 6 months of observations. And I wanted to flash up the scheduling efficiency for this list of 17 stars. So it's not quite as good as when we had our 20 A and B ranked stars before, but it's still not bad. On average, we still have about 75% efficiency across the whole sky. And if you're curious as to how this affects observations of your favorite target, I've overlaid some example targets on here just to give you that sense. I'm running out of time, so I'm just going to quickly talk about HWO implications. So, reference stars could be a problem for HWO if they have, if HWO follows a similar sort of observing procedure, and if it does, those reference stars have strict criteria. So I'm not going to go over each of these in detail, but I really encourage people, especially from the HWO community, to really think about these sort of properties or aspects when designing instruments and also ConOps. Okay, so I'm out of time, so I'm going to leave up my summary slide, and I'm happy to take any questions.
All right, we've got a few questions over here to start.
Hi, this is really great. Is this on? Yeah, okay. This is really cool. I was wondering what kind of proper motions some of these reference stars have, and whether you're thinking about potentially changing background fields and background companions, which especially on the HWO timeline will be very relevant.
Yeah. So, our observation procedure is to not just observe once, and if we see something, move on. We do actually interleave follow-up observations to, assess whether or not things are truly bound or background. In terms of the proper motions, it's actually a pretty good mix of things that are really nearby, so very high proper motions, and supergiants that are extremely far away and so have very little proper motions. And so, we're actively assessing all of that in our observation process. Skylar also talked about our sort of reference star snapshot campaign during the observation phase that will also help us, get a better sense of, how bright some of these background companions may actually be at visible wavelengths, and also where they may be in the future.
We have time for one quick question.
Okay, I'll take it. So you briefly alluded to this before. What matters is how the reference star map onto the early science targets that we want to use for doing technology demonstration. How does that mapping look like for the earliest, easy to detect TTR5 objects? And if someone already has deep enough observations, what is the recommended procedure to contribute that to the CPP team?
Yeah, so we've done an initial sort of test, or we've done initial calculations to assess some of our observation phase targets. So far, nothing is really impacted by reference star availability, at least at the times that we want to observe those science targets. But again, the list is still evolving, and that could change in the future. And in terms of, I think your other question was about how people could contribute to this vetting effort, more or less. Yeah, I mean, I'm always happy to communicate with people outside of the CPP about contributed observations. But yeah, I mean, for the most part, we have a good handle on vetting our reference stars, at least, by this fall. But there are other sort of things going on in the background that I don't have time to get into detail here, that I'm happy to talk more about afterwards, if you're interested.
Well, let's thank Justin again.